So I was asked to give a talk on ventilation and air purification, which we've been involved with for years, but never to the level as this year, because we've kind of, this whole pandemic has brought outdoor air ventilation, filtration, air quality to the forefront of everyone's mind, where before it was, I want to say it was almost like an afterthought. Like people would push like, well, can we use natural ventilation? The code says we can use natural ventilation. We can just open a window, you know? And I'm like, well, you're really not guaranteeing you're getting ventilation by, you know, opening a window and when it's January and making sure you get that right amount of air. So that it's kind of helped in that regard to get people to understand that it's important to have a good mechanical system to allow the building they're in to breathe and kind of, you know, and to keep the quality right. So, so we can go to the next slide, Wes. So I started out basically with ventilation, right? So how do we figure out how much air we need, right? So we typically will go to standards, like the Massachusetts Building Code is currently referring to the International Mechanical Code 2015 for ventilation requirements. It also is very similar to ASHRAE 62.1, which, you know, generally the IMC will cover a lot of it. ASHRAE has some more different types of buildings that the IMC might not call out all the different possible scenarios you may run into. So we tend to use both, but they usually will match on similar type spaces. And then there's other codes and standards, because it's not just, sometimes ASHRAE doesn't really cover, you know, like a healthcare or DPH level ventilation. You might be looking at healthcare codes and healthcare standards to try and determine how much ventilation you need. So we would defer to those other codes and standards to kind of evaluate what we would need. So that's your basic baseline ventilation. Then recently now it's been pandemic, you know, pandemic level. What do we do during this pandemic? How do we adjust basically the code levels? Because the code levels are, you know, basically not enough. They want to heavily ventilate now. So, you know, there's two things that we've been using as we do our studies for these different schools, and it's you know, the ASHRAE Epidemic Task Force Building Readiness Guideline, which it updates every few months. It just updated in October. So it's a very big document. It provides a lot of insight on a lot of different measures, but as HVAC goes, you know, the main crux of it is providing more outside air within the limits of your mechanical systems, right? Because some systems, you can't just provide 100% outside air. It was never designed for that. You know, you may be able to do it, you know, in the spring and fall, but you can't do it in the dead of winter. I bring up an example of, like I saw, you know, several months back, the city of Boston was replacing the windows in the schools during the pandemic, and they were walking through, the newscaster was walking through, and the principal was so proud of the fact that they got these new box fans that they could put in the windows, and then they could turn them around. You know, they could control whether they were doing fresh air or exhaust by spinning the box fans around in the windows. And I was like, you know, that's going to work great for September and stuff, but you know, after November hit, I don't think they're going to be running box fans in the windows. So, but again, so that's, so ASHRAE, a lot of the more outside air, pre and post purge, basically ventilating the building, putting it in an occupied mode prior to 2 hours to 3 hours prior to, and 2 hours, 3 hours after occupancy to kind of flush the space out with as much outside air as you can. And another document that has been referenced and used is the Harvard T.H. Chan School of Public Health, which is talking about pandemic levels again. And they recommend 5+ air changes per hour in a space, which is actually a lot of outside air. That's, if you look at it, you figure a typical office building, you know, 5 air changes an hour might be the equivalent of 1 CFM a square foot, like basically your full supply air. So they're basically recommending that it should be 100% outside air during this pandemic kind of mode. And then they have a very elaborate, and again, it's another, I mean, I could do presentations on each one of those documents, but it's a very elaborate method where they say, well, if you have less than that, you can add better filtration, and that you can come up with a percentage that'll give you the equivalent of so many air changes an hour. Or if you, do something else, you can kind of boost your effective air change per hour in the room by adding certain other measures to it. So that's kind of what we've been using for determining how much ventilation goes into a space. If you go to the next slide, it's really cut right out of the IMC. And it kind of gives you, I mean, this table has definitely changed over the years. I think back in the 6th edition of the code, it was probably just CFM per person. And then come around the 7th or 8th edition, they adopted so much basically in these columns. Like if you look at educational at the very bottom, classrooms, 25 people per 1,000. Each person, you have to figure 10 CFM of outside air. And then every, thank you, Wes. And then and then 0.12 CFM of square foot. So they actually have two measures there. So it's not just like you can have a 900 square foot room and say, well, there's only going to be one person in it, so I only need 10 CFM. You actually have to account for both the square footage of the room and the occupancy of the room in your ventilation numbers. And this is airflow in the breathing zone, and we'll get into that in the next slide about why that's kind of an important statement. But that's the amount of outside air that's in the breathing zone, which is basically from 6 feet down within the room is what they consider the breathing zone. So the only other interesting thing when you use this table is you look at your exhaust airflow rate. You may come up with an exhaust, like for an art classroom, they need 0.7 CFM a square foot of exhaust. So that might actually override your outdoor air requirements, where you might need more than just the 10 CFM a person. You might also need to make up that amount of exhaust, which would actually dictate your higher fresh air level, unless you're pulling it from a plenum or some other source to get that exhaust rate. But that's another variable that comes in place. And this is a few page document. This is just a piece of it that kind of shows how you would determine your outside air. If we go to the next slide. Okay, so this is where the breathing zone becomes really important. And I bring it up because it's actually a pretty, it's something that can be easily overlooked, and it's a pretty important thing when you're trying to determine your ventilation, because a lot of load calcs or ventilation programs, you'll just type in, if you just type in a basic single zone unit, it's going to default that, you have a zone effectiveness of 1.0. But that might not be the case. If you have for example here, if you have a packaged rooftop unit and the supply air coming out of that rooftop unit is 15 degrees higher than space temp, which it probably would be if you're trying to hit 70 degrees, if the air goes over 85 and you have, ceiling diffuses and ceiling returns, now you have to correct your outside air. So you basically have to bring in 25% more outside air than what the table told you to do to meet the code. So that's something that can be easily forgotten. On the same vein, if you have a displacement system where you bring cool air in at the floor and exhaust it high, you can actually take a credit. So you can reduce your amount of outside air because you're bringing the outside air in where the people are, right at their level, so that it's more effective ventilation. So this is something that I just, if you were a mechanical engineer and this is something you do, you might want to just keep this in the back of your head, like what are my temperatures, or how am I distributing to the space, because it may mean that I need more outside air. So that's, I brought that up. If you go to the next slide, I think it's just the next one. Displacement ventilation. So why do we use it? In the schools, we use it extensively in classrooms. And most of the new schools we've been doing for the last several years have been displacement in classrooms. Again, the benefit, we're trying to get the air into the breathing zone. So putting it in low. It comes in very slow, like 50 feet per minute out of the diffusers. Usually they're along the wall, the diffusers. And the air comes in, and then it kind of, just hits the people and kind of blankets them in their dedicated outdoor air, fresh air, tempered, obviously. And then the heat plume takes it up and out of the room. So you don't get, unlike a mixed air system that would really blend the air in the room, right? Mix it up a lot. The displacement system is trying to actually make the air in the room, divide almost like it would in a cooler, where you have hot air, above your head, and you have cool air below. And so there's a few benefits to that besides just the ventilation. You can actually reduce your loads in the room are actually reduced because you're taking a lot of the heat out high. Most of your lighting load is getting drawn out and not getting impacted into the breathing zone of the room, that 6-foot level. So it does allow you to reduce your space. Oh, sorry, that was my last statement. Reduce your space cooling load. And also you can use economizers. I mean, most displacement air, the coolest your air would come in would be like 63 to 65 degrees. So anytime the outside air is below that, as long as it's dry enough, you can use it as economizer, as opposed to like a mixed air system that you might need at 55 or 58 colder. So there's a lot of benefits to it. So we tend to use that a lot in most of our high density classroom spaces. And again, you get your 17% benefit of lower outside air, which is, that until recently, trying to be smart with CO2 demand reset and, optimizing your amount of outside air was what everybody was trying to do to reduce energy costs. Of course, lately now it's gone the reverse, where it's like, no, we want to run everything 24 hours a day. We want to have outside air and, override all the CO2 resets. And that's what we're doing temporarily. But I feel that we're coming back to energy efficiency hopefully soon, because I know we've been burning a lot of power trying to ventilate these buildings lately. So if we go to the next slide, I think I had an example. All right, so this is like a classroom that has displacement ventilation in it. So you can see there's really no grills in the ceiling except the return grill would be up there. This is kind of a hybrid. This is a merged displacement and chilled beam. So usually you see chilled beams in the ceiling, but again, this is a device where your chilled beam is actually built into the displacement diffuser. So you bring your minimum fresh air in, and it'll actually induce a flow equivalent to 3 times what you bring in for outside air, and that'll basically, again, you bring the air in and it's dropping. You're trying to let it spread out along the floor, and then blanket everybody that's in the room. And then if you go to Price Industries website, they'll show if you're sitting there, the fresh air will hit the warm body and start to ride up the person, and it'll go right by their face on the way up to the ceiling as the heat plume takes the fresh air right by them. And again, there's no real mixing of air. So if somebody's breathing or sneezing in their location, it's not like the air is getting blown around. It's basically going straight up and trying to keep the contaminants from mixing with other people in the room. So we found this to be pretty effective as far as ventilation in our classrooms and such. If you go to the next slide, I think. Okay, so humidity. We know it's always been kind of an important thing for comfort, but it's actually now, again, with COVID-19, it's kind of become more of an interesting thing for air quality. What is the impact of humidity? ASHRAE recommends humidity levels between 40 and 50% in the winter, and in the summer between 50 and 60, with like a target of 50%. You don't want to go much over 60 because now you can get into mold and mildew issues, and then 40 to 50% is a very high humidity level in the winter for most. I mean, I would recommend 40. That would be my recommendation. And I think ASHRAE 55 doesn't really mandate humidity control, except on the high end. They do want you to kind of control your high end humidity, but it's not a requirement to humidify buildings. They don't require that. And I think up until this point, it's been a very good recommendation not to humidify, because there's a lot of problems that can come from humidifiers if they're not properly maintained, if they run wild, if they're applied. You really have to. Yeah, I know the Auburn Town Hall went through a major upgrade. It was their humidifiers. They went wild. They got mold spores throughout the building. They had to abate the whole building, and it was closed for like months to do it. And it was all because of the humidifiers. So it's definitely something. If you're going to put them in, you want to maintain them, and you really need to consider the building itself, because older buildings probably can't handle the humidity. Like where we were, Salem Housing, the existing building, you wouldn't want, those old windows, if you tried to put 40% humidity in there, they'd be raining all over those windows, right? Those aluminum, non-thermally broken. So you have to be careful with the humidity and getting it pushed into the wall and creating dew points inside the wall. So it's a great idea. It's great. It's just something that I think we want to be, you have to be careful with it if you're going to add humidifiers to your even in your house. I'd say set it to 35, 40% tops, and just if you got a newer house, you should be fine, and then and leave it at that. So that's kind of, now the next slide will kind of show you why humidity is becoming more important, besides just comfort. I believe it's the next slide. Punch that up, Wes.
Okay.
Yeah. So this is out of ASHRAE. This is an older one this is an old table, but they actually have a new one that is kind of a curved graph, but this shows it fine. Basically, what it's showing is that 30 to 60% range, and how actually bacteria and viruses don't really like humidity. Whoop, no problem. So, and that's why humidity is becoming more important in the COVID world, right? Because we're seeing like, well, wait a minute. Now this does, I want to, qualify this chart by saying it doesn't mean that, boy, if I keep my humidity at 50%, I'm virus free. That's not the case. I think really what it's trying to reflect is what happens to, viruses when you go beyond those ranges. Like it gives it a more optimal ability to grow and spread when you're up into high humidity levels or very dry levels. And I think some of that has to do with, in the dry end, the virus comes out of somebody and it's moist and it's attached, big particle size because it's wet. And then if the air is really dry, it dries up, and now it's the raw virus, right? And it's super small and it can get through almost anything. So there's that issue. And then also just the human body itself. You get very, your mucose membranes, and just, things dry out. You can't filter things as good. And so there's an effect on the human person as well as the actual virus on what occurs when the humidities are outside those ranges. So that's kind of why this humidity topic is in there for air quality issues. So that's that aspect. And if we want to go the next page, I forget what I had on the next slide. Okay, so now we get into filtration, right? Particulate filters. How do filters work? Air filters. That's what we're talking about. So they basically, right? It's kind of like a strainer, right? You're trying to, if you make the filter media tight enough, any particle that's too big, it won't fit through. Basically, it's gonna get stuck in the mat, and that's how it's gonna be blocked. Then there's also impingement, which basically means whatever's flying through the air just smacks into the fibers of the filter and gets stuck to the filter. Usually, the filter medias will have some kind of a sticky substance on them to try and propagate that particles hitting them. Interception is kind of like they're just grazing the fiber of the filter, so they're just going by and they catch the edge of it. So the particle's small enough to get through the filter, but it's just getting, as it goes through all those weaves, it's not going to make a clear shot, so it's going to hit something along the way. So that's basically what interception is. And then the chaotic motion, Brownian. The next slide actually shows this better anyways, but the Brownian diffusion is basically the air gets into the filter and it starts getting all turbulent, so it starts bouncing around, so it basically causes the particle that you're trying to capture to slam into the fibers. So that's basically how you can, get a filter that may not be able, like a MERV, the big recommendation nowadays is MERV 13, put MERV 13. Well, a MERV 13 filter really isn't tight enough to catch viruses. So how does it work? Well, it may not be able to catch them as a sieve or a straining method, but it's catching them by the other methods, and that's kind of how that's occurring. So if you go to the next slide, Wes, you'll see, I think, yeah, that's just kind of a graphic of what's going on. So the big circle in the middle is basically a fiber of the air filter. So you got the sieve approach where the particle just won't fit through the fibers on the right side. The impaction, where it just slams into the fiber and gets stuck. And then the interception, which is the second one from the left, which it's just kind of going by and gets hooked on as it goes by. And then the Brownian diffusion, which basically causes an impaction. It basically turbulates the air and it slams into one of the fibers in the filter. So that's kind of what we're trying to accomplish with an air filter, not just making it so tight that the particles can't possibly fit through, but making it so that they can also get captured from some of those other methods. So if we go to the next slide, we'll see, what do we got? Next slide is, okay, so this is right out of ASHRAE, but again, most filters up until this year, MERV 8 was kind of a common, good quality filter, or used to be considered a 30% filter, common in commercial buildings. Since the pandemic, we've kind of, ASHRAE has gone to recommending MERV 13. You can see it's a much higher level, from 30% to basically 90% efficiency. So it does make a huge difference. The thing with putting MERV 13 filters into existing systems is you just have to be careful about what the effect on the initially out of the gate, like a MERV 8 filter and a MERV 13 filter have pretty similar pressure drops, but but the MERV 13 filter will get dirty much faster. So if it doesn't have a MERV 8 in front of it, and you're just taking a MERV 8 out and putting a MERV 13 in, that's going to fill up pretty fast. And what you might end up having is less air moving to your space, and then you'll kind of go backwards with what you were trying to accomplish, right? You want to keep ventilation rates high, and now you put a better filter in, but you've lowered your ventilation rates, and that wasn't a good thing. So you just basically want to keep your, look at what you're putting the equipment into, and then with the filter into, and then and go from there. And then again, once you can get all the way to like 16 as a like a cartridge type filter, and then above that you kind of move into the HEPA range, where you're a MERV of 20, and then there's even ULPA filters, which are very rarely used, but they're used in like really high level clean rooms and such, where they can really tight filtration. So that's the basics of the filters there. And we can go to the next slide. Okay, so after filtration, something that's been vetted for many years is UV light, right? And UVC, meaning it's a C band of light, UV light, just higher, just above, I think sunburn level is one above, and then there's UVF is on the other side of it. But so UVC light has been used a lot in HVAC over the years, but mainly it was used for keeping your coil clean, keeping that mold and bacteria from growing on your cooling coil. So it was used in that application, not necessarily to try and sterilize air. Not that it wasn't used that way. I mean, obviously in hospitals and applications like that, it was used, but for general commercial HVAC, if you had a UV light, it was probably stuck right up against the cooling coil, and its purpose was to keep that coil clean. You can also, the thing with UVC light is, the virus has to be exposed to it for a certain amount of time. So if you have just one UV light at the filter rack, right, maybe the air is moving about 500 feet per minute. So it doesn't spend a lot of time in that light. So you realistically either need to slow that air way down, or you need to put like multiple UV light bars for maybe 50 feet in your return air duct to try and clean that air. So that's one of the considerations of UVC light in using it. It's definitely something you want to use, but I think a lot of the applications where you see it used in like portable air cleaners and stuff, they show the UVC light in there. And also even in these is that, okay, if the virus gets captured by the HEPA filter or the filters in the unit, the UVC light will then kill it immediately. It won't have to wait and die after a few days. It's gonna die, after continued exposure to the light. So that's a very common thing now. UVC light we've been seeing employed. And if you go to the next slide, I think it just shows a picture of a.
If I could jump in here, because it seems like UVC is something that has applications outside of the pandemic. Like,
oh yeah,
why wouldn't we do this, right? It keeps the coil and the pan clean. It's going to save on maintenance with a bit of a, obviously equipment and energy cost.
Yeah.
But Wes and I have been concerned for a while about energy recovery ventilators that use a wheel, because you kind of get stuff that flows out and maybe sticks to the medium, and then we're sucking it back in the building. And would UVC be something that we'd want to combine if we're using a wheel?
It would, yeah. I mean, the wheels generally you should have filters on each side, and then their theory is, well, if you blow through, it's going to clean the other way. Granted, you're going to have some carryover, right? As if you got something that gets in there, so it's kind of a self-cleaning process. But the UVC light will certainly not hurt it. The only thing I will say is you want to make sure wherever it's going in the unit that it's not exposed to things that are going to get degraded by the UVC light. Like, make sure the wheel is made of a material that's not going to break down, because they can certainly, there's certain materials, I forget, I was looking at them at one point, but that'll just get, either super brittle or just totally break down as the light just sits there and bakes on it, basically gets it. It's almost like a continuous sunburn. But yeah, no, I mean, that's why they were put on certain coils that, right, keep the coil clean, keeps the efficiency up. If you keep the coil clean, the efficiencies are up. So there's definitely, I mean, it's just maybe every 2 years you got to change the bulbs and things of that nature. So, but it's just a maintenance item.
I'm glad you brought up the idea of can material take it, because one project I was working on, we were looking at putting UVC in the air handlers, but we couldn't do that because all the insulation on the wiring would have gotten fried.
Right. Yeah.
So
yeah, you gotta.
Some insulation can handle it, some can't. And
right. Yeah. So yeah, no, definitely got to be considerate of that. So
apparently, insulation on the wiring is a big deal. I don't know.
Yeah. I mean, inside a unit, it maybe it'll be metal clad or plenum rated, but again, I don't know if a Teflon plenum wire will resist UVC light. That would be something you just want to be careful of when you apply it. So, because we were doing one job in Boston where we had like no return duct, and we were and the units it was like those package units. There was no room to put a UVC light in, and we were actually considering like putting them, the mech room was a return plenum, and we were looking at like, maybe we should just put UVC lights in this room, but then we were getting concerned with what's in this room that's going to be exposed to the light, and we'd have to have a door switch, because if somebody walks in, you want the UVC lights to go off. You don't want them to get burn their eyes out because they're looking at UVC lights. So it's better applied inside a unit or in a duct where there's no chance of people staring at it and hurting themselves. So, Wes, if you want to go to the next slide, I think I should show a picture. Yeah. So there you go. There's basically, you got the coil with the drain pan on the left, then you got the filters, so the air is coming from the right, and so basically the lights are continuously exposing the coil and the downside of the filters to light, and the pan itself in the bottom, so it keeps any mold and slime buildup from going, and that's kind of how how it would be put in a unit, and that's a good spot for it, because it's probably the slowest the air will be in the unit, right at the coil. You're trying to slow things down. The filters, you can't really go much higher than 350 to 500 feet per minute. So that's the spot you want to kind of put it to keep the air the slowest. So, and then if you go to the next slide, I think that brings in, oh yeah, this is just a Train offers this, and actually some of the portable air cleaners on the market are doing this now. So it's basically there's a catalyst made out of titanium and other various metals that the UV light will shine on in the filter, and will basically create these hydroxyl radicals, which will basically go out into the room, and they kind of kill viruses and stuff like that. So that's something that I've seen. I got this off of the Train literature. This is something they propose in their much bigger air handlers, like for hospitals. They put this photocatalytic oxidation UV bank in the unit, and that would basically be something to. So the UV light is not only, it's really creating free radicals, if you will, from the catalyst, instead of just relying on the UV light to kill things. So it's kind of doing a dual action. So that's I just threw that in there. I haven't seen this much used, but it's definitely, I've seen it in, I think the city of Chelsea, which I was doing reports for. They just bought a ton of these things that have this catalyst thing in it. So it's something that else that's out there. So, and then if you flip to the next slide. Okay, so this bipolar ionization this is getting a lot of traction lately, and I've taken kind of it seems very positive, but I've taken a kind of a neutral aspect to it. I do recommend it, but I don't.
It has its pluses and minuses.
Yeah, correct. So you're basically creating positive and negative ions, right, in the air, and polluted air has less. Right. So I got you. So, and they're real unstable too,
Just like that.
Yeah. So basically, you're making ions in the air. So these have been used, for decades in places like TD Garden has them. Casinos use them a lot. Basically what they were meant to do is just clean the air, right? So it's meant to go out, and instead of waiting for the filters to clean the air, it's going out and it's causing all the smoke in the casino and all the dust in the convention center to bind and become so big that it will fall out of the breathing zone, basically fall to the floor, or if it gets picked up in the HVAC system, it's big enough that filters will actually grab it, because it's made the dust and part of it. So it's made, now all of a sudden, maybe your MERV 8 can act like a MERV 13 because you're making all the particles big enough for it to for it to grab. So that's kind of what it was meant to do. With COVID, when COVID hit, they started studying it more, and they found it seems to be very effective with basically neutering the virus, if you will. So it limits the virus's ability to infect. So they've done some studies on this, but basically ASHRAE refers to Center for Disease Control in this regard, and they're kind of saying they're looking at it as an emerging technology because, again, it's been deployed for years, but now they're looking at it for virus mitigation. So it looks promising. I mean, I know RPI in New York did their own studies in their own lab and determined that, they really liked what they saw, so they were going to order, I think they went ahead and ordered, for their whole campus, these ionizers. So they're definitely, it's definitely promising. So I usually tell clients that, look, it's another tool in your kit. You could put this in there, and at least it's going to help clean the air and make your filters better, and it may attack the virus in the room. The studies they show say that it can kill or neuter 99% of the virus within 30 minutes in a room. So that's a pretty bold statement, but that they're basing it on the early studies that they've done so far. So that's kind of what bipolar is. If we switch to the next page, I think it just shows So Atmosphere is one of the makers of these bipolar ionizers. Sorry.
Part of the presentation.
Yeah, she thinks somebody must have pulled into the driveway. So basically, this would go in the air handling unit. It would, and it wants to go right at the discharge, or in the supply duct. So downstream of any filters, unlike some of the other filters are upstream of things. Hold on a second, I'm going to just shut the door. She'll just bark and we'll see what happens. But so it goes downstream of all the obstructions because we don't want it to bind with all these other things that it could get, all these ions can get hung up with. So basically it goes downstream and it enters the rooms, and ions don't last forever. So there's a half-life. They may only be lasting minutes. So, it gets generated, it goes down the duct, it enters the room, it binds with, what's in the room, makes things clump together. Basically, the whole idea is, all right, the virus is floating around. If you create a charged particle, that's going to attach to the virus, and then things are going to attach to that, and it's going to clump together. Basically, it makes the virus big enough to get filtered out, or makes it big enough to drop out of that breathing zone, make it drop to the floor or something, so it can get stuck to somebody's shoe on the way home or something. I don't know. So basically, but as it's now that it's bonded to the virus, the argument is it's damaging the virus. So if you go to the next slide, I think you'll see. Again, this is, I think, from Atmosphere. So on the right, you'll see the slide is showing, the ions come in, and then they start to bind with, they make a positive and negative charge, and then they start to clump together, right? All positive and negatives start sticking together, make it bigger. On the left, this is the claimed reaction on the viruses, right? The ions go, and they basically interrupt the outer shell of the virus and cause it to basically not be able to infect people. So that's some like the city of Worcester invested huge money in putting ionizers in every one of their schools. They have, I think, Honeywell, they have an energy services contract, and they're going and putting it in all their schools right now. They make them to go in univentilators. They make them. So they've definitely bit the bullet on this. So it's definitely something that's out there. It seems, pretty reasonable. There is, if you talk to the UVC people and the ionizer people, they will duke it out over whose is better, and you don't know what the ionizer is doing to, what it might be converting a molecule to, and which is a valid statement, and then the UV people will be like, the other argument. So you do see a little bit of that back and forth. But so this is what we've seen used a lot. And then if we go to the next slide, I think it's just an example of. All right. So now this is a very big installation, but this is basically this should be a supply plenum. So that might be a heating coil there, because I see the freeze stat tube, or maybe it's an averaging. But so the air would come out from the left and then just enter that supply plenum and then drop, down to the airflow. So obviously on smaller systems, it may just be one of those tubes sticking into the side of a duct. You drill a hole, you stick it in, and this is obviously a pretty sizable air handler, because that's quite a number of ion tubes. And again, like UVC light, these have to be changed every 2 years. That's not the case with all ionization systems. There's needle point ionization, which doesn't really need that. However, there is some maintenance required with keeping the needle points clean. Otherwise, if they get dirty, they stop generating ions. So there's other, and again, those two makers duke it out over who's got the best mousetrap, basically. So if you go to the next thing, I think this is almost the last slide. Okay, so portable air filters have been very used widely in the classroom environment to try and get these schools to reopen. This is called Price Industries makes this. It's called room air purifier wrap, they call it. And basically, it's just a HEPA and a fan. So it stands in the room, and it's a HEPA filter, and it brings air in, and it blows it out. The only difference with this is they do offer ionization. They have a needle point ionizer in there, and they also offer UVC light. So you can actually have all three technologies if you want. The Harvard TH Chan is kind of recommending just, if you get one of these, just focus on the HEPA, right? Get the HEPA filter. Their comment with that is just, look, we don't know all the interactions that may occur with, the UV lights and the catalysts and the ionizers. We don't know, like, maybe there's something in that room that nobody knew about, and it's, I don't know, an open bottle of whatever, Ajax or something, and it reacts with something and creates something that you didn't expect. So that's kind of their tact is like, look, just put the HEPA filters in, focus on that, but to the other point, if you put the ionizers in, you could do one air handler, and you could do an entire floor of the building and try and provide better quality air for that floor of the building. So it's definitely, there's just a lot of different ways to attack what's going on. And I think that's the end. I think my next slide does it say end?
End?
Yes, it does. Yeah, that's it.
There we go.
Hope I didn't take much time. Jeez. So